This is a good question on Cauchy integrals, and we're going to do it with two methods. First of all, Cauchy integral formula for derivatives, and secondly, the residue theorem. But the first thing we've got to do, regardless of which method we use, is we are going to have to check whether or not any pole is within this region here. And so to do that, first of all, what we need to do is understand what this is. So e to the I theta is basically a unit circle of radius 1 centered at the origin, and then 1 plus that basically just moves it right by 1. So let's draw our circle here, and then basically what that means is that this point here is the origin, here is our real, here is our imaginary, here is the center of our C, and we are traversing C anti-clockwise, and there is C there. So that's the first thing we've got to do, is work out what the region is. The second thing we're going to do is just rewrite our integral slightly as 1 over 2 pi I, the integral around C of sine z squared over z minus 1 squared dz, which is only a tiny little amendment, but what it does do is make it very clear that we have a pole here at z equals 1, pole singularity, and the order of the pole slash singularity is order 2, and we need that for regardless of which method we use. And finally, z equals 1 is clearly inside the circle about which we are integrating, and so therefore we need to use the residue theorem or Cauchy's integral theorem for derivatives. Okay, so let's go. I'm going to do them. I'm going to try and put them side by side. So this one here is the Cauchy integral formula for derivatives, and on the right hand side I will do the same thing but with the residue theorem, because they're very tiny bit different. Obviously they give the same answer, and the residue theorem is basically just a generalization of the Cauchy integral formula for derivatives anyway. But so what we got to do, let's look at the formula for this. So basically that would be fn of a equals n factorial over 2 pi I, the integral of f of z over z minus a to the n plus 1 dz. That's Cauchy's integral formula for derivatives. Okay, and basically what we're going to do in this one is we are going to let f of z be equal to the bit that doesn't include the pole, i.e. sine squared z, and we are going to let a equal 1, clearly, because that's where the pole is, and we are going to, this is important, we're going to let n equal 1, because in the formula here, the pole, if the pole is of order n, then basically we let n in the formula be n minus 1, and so therefore if the order is 2, we take n equals 1, which means therefore that we only have to take the first derivative of our function f of z, that means the first derivative or nth derivative, and the first derivative of f dash of s is 2 sine z cos z, which equals sine of 2z. Okay, so therefore we have that f dashed at 1, or a, which equals f dashed at 1, is equal to sine of 2 times 1, which is sine of 2. Okay, so now all we need to do is just fill that formula in there. So we have that sine of 2 equals n factorial. Okay, well n factorial is, we've given n is 1, so that's 1 factorial over 2 pi I. The integral f of z is sine squared z over z minus, and a we said is 1, squared dz, and that is actually the integral that we seek. If we look at the question, that's the integral that we seek here, and so therefore the answer to it using the Cauchy integral formula for derivatives is equal to sine of 2. Okay, so we've done it using the Cauchy integral formula for derivatives. Very easy. Now let's do it again, but this time let's do it with the residue theorem. Okay, so basically residue theorem, we have that the residue, here's the formula of AF equals, it looks a little bit more complicated and I'm probably not going to be able to fit it on, 1 over n minus 1 limit, okay, so the limit as n approaches, as z approaches a, and I have to put the limit down here, sorry about that, d n minus 1 dz n minus 1 z minus a to the n f of z. Okay, but there's some slight tiny amendments here. because the f that we deal with in the residue theorem is slightly different from the f that we deal with in Cauchy's integral formula for derivatives. Okay, so basically in the residue theorem, the whole thing is our function. So in the residue theorem, f of z is equal to sine squared z over z minus 1 squared. And n in the residue theorem is equal to 2. So basically it's a slight difference from n equals 1. Even though the order of the pole, obviously it's the same integral that we're doing, the order of the pole is 2. When we're using Cauchy integral formula for derivative, we put n equals 1 minus, the order of the pole minus 1. And in the residue theorem, we actually put n equals the order of the pole. Okay, so basically now what we need to do is that the residue of 1f is equal to 1 over 1 factorial, because n is equal to 2, times the limit as z approaches 1 of d dz. We only have to take the first derivative because n is 2, so that basically gives us the first derivative of z minus 1 squared times our function, which is sine squared z over z minus 1 squared, and they cancel each other out, which just leaves us with the limit as z approaches 1 of d dz of sine squared z, and now this is beginning to look mighty like the left hand side, and that basically equals the limit as z approaches 1 of 2 sine z cos z, which is the limit as z approaches 1 of sine 2z, which equals sine of 2, just putting z equals 1 in there, and that is the residue of the singularity at z equals 1. But in this particular case, there is only one singularity, and therefore there aren't any residues to add up except for this one. And so basically the integral here is just equal to the residue that we find at z equals 1, which again is sine 2. So both methods give the same answer. Obviously, if there was more than one pole, then we would have to use the residue theorem. But when you've only got one pole or singularity, personally, I find the Cauchy integral formula for derivatives, or the Cauchy integral formula if the pole is of order 1, to actually be slightly quicker and easier to use than the residue theorem. But I guess it's just a personal preference there. Okay, well, I hope you found this useful. If you have, please like this video and subscribe to the GRE Academy YouTube channel. Thank you.